Now let's take one question. This is very important. We have a wedge of mass capital M, and on this wedge I have kept a block of mass small m, and the angle is theta over here, and this is the surface. There is no friction anywhere. You don't have friction anywhere. Since I have not taught you the friction, I am not using any friction in my question. So there is no friction between the wedge and the block. There is no friction between this wedge and the surface. That's the question. So here you have to find out, the acceleration of block of mass m with respect to wedge. You have to find the acceleration of the block of mass m with respect to wedge of mass capital M, right? You have to find this. We have to find the acceleration of this block of mass small m with respect to wedge of mass capital M. So the first thing you do over here is you have to draw the free body diagram. You have to draw the free body diagram. So let's draw the free body diagram of both the body, right? Let's see what is the free body diagram for the wedge. For the wedge it will be. So let's draw the free body diagram, right? Here the wedge interact with the earth, so you have mg. Earth is constrain the motion of the wedge in downward direction, so you have a reaction R. Alright, this block is also interacting with the earth, so you have the force mg acting on this block. What else it interact with? It interact with the wedge. And what wedge is doing basically? Wedge is constrain the motion of this body in this direction. Wedge is constrain the motion of this block in this direction. It will constrain the motion of this block in this direction. So you have a normal reaction acting on the block in direction opposite to the direction in which wedge constrains the motion, right? You are going to have a normal reaction in direction opposite to the direction which you have the motion getting constrained, in direction opposite to the direction in which motion is constrained. So who applies this normal reaction? This normal reaction is being applied by the wedge, right? So as a reaction, this mass is going to apply a normal reaction N over here, right? Do you have any other force? If you want to see whether you have applied all the forces or not, you just see with what this block is interacting. This block is interacting with the earth, so you have a force over here. This block is interacting with the wedge, so you have a force corresponding to that over here. So to every interaction you will have a force in the free body diagram. This wedge is interacting with the earth, so you have mg over here. The wedge interact with the surface is constrain the motion, so you have a reaction R. The wedge is interacting with the blocks, so you have a normal reaction N over here. Alright. Now, so this is the free body diagram. This is the free body diagram. Now I ask you one question. Can I shift this force from this point to this point? Can I shift this force instead of showing it over here? Can I show it over here? Is there any problem? If I don't show the force over here, can I translate this force? So can I shift this force from this point to this point? See the block is interacting with the wedge at this point. So as a reaction, block applied force N on the wedge over here. But I have shifted this. Is it right? That's the question. See, we are into a part of mechanics which we call particle dynamics. I'll tell you why we can do that. We can do that, but let me explain to you why we can do that, right? So we are into particle dynamics. See, when do you call a body to be a particle? When do you call the body, when the body is treated as a particle? When do you call the body as a particle? See, the dictionary meaning of particle is something which do not have any extension space. Something which do not have any extension, do not have any volume. In true sense, in physics, it is only electrons which can be called as a particle, because they almost no volume, or they have very negligibly small volume, negligibly small extension space. They are electrons basically, right? So in this case, but these are not electrons, they are much bigger particle. But in mechanics, when do you call the wedge to be a particle? When do you call it to be a particle? When do you treat this to be a rigid body? That's a good question over here. See, we are in mechanics, we are basically studying effect of the force, and force as such has got two effects. One is translational effect and other is called rotational effect. It has got two effects, translational effect and rotational effect, right? If you apply a force on a body, say a body of mass m, if you apply a force F, it has got two impacts. It can accelerate, it can rotate about this point. If you apply a force on the sphere, it can translate, it can rotate. So we are into we study the translational effect. Translational effect is all about the change in translational state when a force F acts on the body. Rotational effect is all about change in rotational state of the body when a force acts on it. So when a force acts on any body, it produces both change in translational state, it also produces change in rotational state. It produces change in translational state and rotational state both. When you talk about change in translational state, then in that case, the change in translational state is characterized by what we call acceleration. If you apply a force, if change in translational state is characterized by vertical acceleration. This acceleration only depends on the magnitude and direction of force. The acceleration only depends on the magnitude of force and direction of force. Because if you apply the force over here, you have the same acceleration. If you apply the force over here, you have the same acceleration. If you apply the force over here, you have the same acceleration. So acceleration does not differ. Acceleration is same regardless of the point of application. So acceleration depends only on the magnitude. It depends only on the magnitude of force, and it depends on the direction of force. It depends on the magnitude. It depends on the direction. Alright. It does not depend on the point of application. The acceleration change in translational state does not depend on point of application. It does not depend on the point of application. It only depends on magnitude of force. It depends on direction of force. It does not depend on point of application. So in that case, there is no harm if I treat this block as a point particle. There is no harm if I treat the body as point particle, something like this. A force F acting on it. If I treat the whole body as point particle, there is no problem. I can treat the whole this block as a point mass F acting on it, and acceleration equals to F by m. So when you are into translational effect of the force, you can treat the whole body as a point particle, and we are into translational effect of, we are studying right now, we are into particle dynamics. We are studying the translational effect of the force. So this whole wedge can be seen as a point particle, and there is no harm if I shift this force from this point to this point. So I can shift the force from this point to this point, because the direction of the point of application does not play an important role, does not play any role in the change in translational state. It doesn't have any effect on the translational change in translational state. So I can shift this force from this point to this point or any point. Okay, it does not depend on point of application. Whereas if you are interested in rotational effect of the force, it does impact. If you are studying rotation of this body about this point, the point of application does matter. In that case, point of application does matter. So its rotation does depend on the point of application. There you can't treat the body as a point particle. Body has to be treated as a rigid body. That we will see in the chapter of rotation. So I can shift this force. I can shift this force, right? I can shift the force from this point to this point. Okay, right. Now let's solve the question. This is your free body diagram. This is your free body diagram. Now suppose the first thing you do in any mechanics problem is you draw the free body diagram. You draw the free body diagram. The second thing which you do is you choose the first thing you do is you draw free body diagram. The second thing which you do is you choose coordinate system. You choose the coordinate system because see, you are not going to apply the Newton's second law in vector form. You are not going to calculate the vector sum of these three forces and then you apply this law. You are not going to do that. You are going to apply it in component form. Basically, you break it into three scalar equation: fx equal to max, fy equal to may, and fz equal to maz. You break it into three scalar equation basically, right? So when you are applying this Newton's second law in component form, you must first define what is x-axis, what is y-axis, and what is z-axis. And for that we have to choose a coordinate system because we want to apply this Newton's second law in component form. Alright. So when you choose the coordinate system, you have certain consideration while choosing the coordinate system. You have certain considerations while choosing the coordinate system. What are those considerations? First consideration is you choose the coordinate system in such a way that most of the forces should lie along the coordinate axis. Most of the forces should lie along the coordinate axis. The acceleration should also lie along the coordinate axis. So you should choose the coordinate axis in such a way that most of the forces should lie along the coordinate axis. The acceleration should also lie along the coordinate axis. Why we want this? We want this because all those forces which lie along the coordinate axis, they won't be resolved. We don't need to resolve them. And those forces which do not lie along the coordinate axis, we have to resolve them while applying these equations, right? So the less number of forces we want to resolve, that will be easier, that will be better for us. If we have to resolve less number of forces, that is better for us. So we should choose the coordinate. These are not like compulsion for us. They are just because that way, if you do it accordingly, if you do it like this, if you choose the coordinate system having these considerations, then your equation will be simpler. The equation will be simpler to solve. This equation will look to be simpler. Otherwise, you are free to choose any coordinate axis. You are free to choose any coordinate axis in that case. Alright. So I must choose a coordinate system. I must choose a coordinate system with this consideration, and that really helps you. That really helps you. It simplifies the equation. You need to resolve less and less number of forces. Alright. So let's draw the coordinates. But before that, let's get some idea about the acceleration. Suppose we have the observer over here on the surface. So how is going to observe what observation he makes about the acceleration? The eyes and nose and mouth. So what observation he makes about the system? Where will he find what kind of motion he see in this block and what kind of motion he see in this wedge? Obviously he'll see this is N is uncompensated force. By geometry you can prove that this is theta. So N has got a uncompensated component. N has got a component backward direction. He will see the wedge moving in backward direction with, say, the acceleration capital A, and he will see what kind of motion he will see in this block. Along with the wedge, this block moves in with A in backward direction, and this block also moves with respect to wedge with an acceleration small a. He will see an acceleration A in this block wedge, and in this block he is going to see an acceleration, one acceleration A along the with respect to the wedge, and an acceleration capital A along with the wedge, an acceleration capital A along with the wedge. Alright, he is going to see two acceleration. Since it is lying on the wedge, this block is going to inherit all the acceleration which the wedge is having, and apart from this acceleration A, he is also going to see an acceleration small a with respect to the wedge. Alright, so he will be seeing two accelerations, one small a and another capital A. Alright, so he will be seeing these two accelerations. Now let's draw the free body diagram. Let's draw the free body diagram. I can draw the free body diagram like, sorry, not free body diagram. Let's draw the coordinate axis. So I can draw this coordinate axis. Alright, if I draw this coordinate axis, one of the force is going to lie along the coordinate axis. Out of two, I'll have one lying along the coordinate axis, and here out of three, I'll be lying two of them along the coordinate axis. So I can take this coordinate axis. Alright, I can take this as x-axis, y-axis. This is x-axis and this is y-axis. Whatever coordinate axis you choose for the forces, you choose the same coordinate axis for the acceleration also. You choose the same coordinate axis for the acceleration also. Like, let me shorten this part. Right. So you choose the same coordinate axis for this also. This is x and this is going to be y. Alright. Your coordinate axis on this side and on this side should not be different. Alright. Okay. So see here, if I choose this coordinate axis, out of three forces, two are lying along the axis and acceleration is lying along the axis. Here out of two, one force is lying along the axis and one of the acceleration is also lying along the axis. Alright. So we have drawn this coordinate axis. Now we can now write the Newton's second law. We are in position to write Newton's second law. So the third thing we have to do is we have to apply Newton's second law. Newton's second law. We can apply Newton's second law. Alright. Alright. We can apply this Newton's second law. So this is an angle theta. So let's apply Newton's second law separately on these two. Once you draw the free body diagram, they will be behaving like a separate particle. Alright. So you have the acceleration. There is no acceleration of the wedge in y direction. So the net force in y direction should add to 0. R minus mg. What is net force in upward direction? R minus mg minus n cos theta equal to 0. You don't have any force, you don't have any acceleration in y direction, so net force in y direction should also be 0. Now here in this direction, let's suppose the wedge is accelerated with A. What is the net force in backward direction? The net force in backward direction is n sin theta, and that should be equal to mass into acceleration. Here you have the net acceleration in x direction is going to be small a minus capital A cos theta. What is net acceleration in x direction? Small a minus capital A cos theta. The block has got two acceleration for this observer. The block is moving along with the wedge because it is on the wedge, so it is going to inherit all the motion of the wedge. It is moving, it is going to move with respect to wedge also with an acceleration small a. So net acceleration in x direction is going to be small a minus capital A cos theta. And what's the net force? Net force is going to be mg sin theta equals to m into A minus A cos theta. And what is net force in y direction? You have what is the acceleration in y direction? So you have an acceleration, a component of capital A in negative y direction, that is A sin theta. And what is net force in negative y direction? That is mg cos theta minus A equals to ma sin theta. So these are the equations. And now the fourth thing is very easy, and that's part of mathematics. You have to solve the equations. So you can solve the equations and you can get what is small a and what is capital A. Alright. Okay, so you can do this. You can do this. Now there is a big question. What's that big question is? How will you solve the question if I have observer over here? If your observer is here, let's call it O1. I have solved the question as per O1. And now I want to solve the same question with respect to an observer O2. What's the difference between the two observers, O1 and O2? See, O1 is an inertial observer. O2 is a non-inertial observer. What is inertial observer? First of all, tell me what is inertial frame. Since this word has come for the first time, I'll define what is inertial frame. Right? Inertial frame is a frame which is non-accelerated and non-rotating. It is non-accelerated and non-rotating frame is called inertial frame. A frame which is non-rotating, non-accelerated and non-rotating. Even I don't have the need of writing non-rotating, in fact, because rotating frame is always an accelerated frame. Ideally, there is no such frame exist in nature. Ideally, don't have any body which is non-accelerated and non-rotating. Even Earth is also spinning and revolving around Sun. Earth is rotating and revolving, so Earth is also accelerated frame. Every celestial body is accelerated frame. Every celestial body is rotating and revolving around certain thing. Ideally, such a frame do not exist. But for the sake of mechanics, if I want to take some inertial frame, I take a frame attached to distant stars which seems to be not changing their position as an ideal inertial frame. For this current chapter, I'll take Earth as inertial reference frame. For this chapter, I'll take Earth as inertial reference frame. So this observer, if your S is an inertial frame, like I've taken Earth as inertial frame, I take suppose a frame attached to Earth as S. Suppose there is a frame attached to Earth as S, so S is an inertial frame, right? If S is a frame attached to Earth, so that will be inertial frame. I am assuming Earth to be inertial frame. Now any frame S attached to Earth is going to be inertial frame. And any frame which is either at rest with respect to S or moving with constant velocity with respect to S will also be inertial frame. If S is inertial frame, then any frame which is either at rest with respect to Earth or it is moving with constant velocity with respect to S will also be inertial frame. Alright. So O1 is inertial frame. O1 is someone who is attached to Earth. Right. O2 is not an inertial frame because O2 lies on a wedge and wedge is accelerating with respect to this O1. So O2 can't be inertial frame. So if O2 is not inertial frame, what does it mean? What does it mean? Actually what happens is your Newton's law holds good only in an inertial frame. Only an observer who is inertial can correlate his observation of acceleration with the forces. See, why is it so? See, you have F equal to mass into acceleration. F is a force which is physical reality. The force F arises out of interaction. Force F arises out of interaction. So the forces are going to be same for O1 and O2. O1 and O2 won't find any difference in the O1 and O2. O1 and O2 won't find any difference in the interaction that is taking place in the system. O1 and O2, they are not going to find any difference in the interactions that is taking place in the system. Hence, the free body diagram they are going to draw is same. So the forces they observe is same. That's not observer dependent quantity. I am not talking pseudo forces. I am only talking about real forces which arise out of interactions. Since the interactions which are being observed by O1 and O2 are going to be same, the free body diagram they are drawing is same. The forces they are observing is same, right? But there is a difference in acceleration. What observation O2 makes? See, O2 is lying on the wedge, so he is not going to see this acceleration. He will find the wedge to be at rest, and his observation about this mass is also quite simplified. He is going to see only this acceleration A. He is going to see this wedge, this block to be moved with acceleration A. Since he is finding the wedge to be at rest, he will only see this acceleration. So his observational acceleration is different. It means for O1, if I write F equal to ma1, and for O2 I write F equal to ma2, in that case one of the equations is wrong. Reason being, both are going to observe the same force. Both are going to observe the same force, but they are observing different accelerations. So how can a same force be equal to both ma1 and ma2? F is same for both the observer. So how can the same force be equal to ma1 also, and how can it be equal to ma2? And Newton's law makes it very clear that this law holds only for the observation made by O1. This law holds only for observation made by inertial observer. So only this is true and this is wrong. This can't hold. Newton's law does not hold for non-inertial observer. It holds only for inertial observer. It holds only for inertial observer. Newton's law won't hold good for this O1. Alright? Okay. So what's the way out in that case? Sometimes you are destined to be a non-inertial observer. So how will you solve the problem correlating the observation made by O2? There is a way out. The way out is, see, I can't make O2 understand that you have an observation, you have some acceleration of the wedge. But he is not observing the acceleration of the wedge. So I can't say O2 that, look, you have acceleration in the wedge, because he is not seeing acceleration. Every observer is true to his observation. What he is observing, he is telling you that. But since O2 is non-inertial, he cannot correlate his observation with the force with respect to Newton's law, with respect to force using Newton's second law. O2 is seeing this force. See, he is seeing this normal reaction N. He is seeing that you have a component of N in backward direction, but then he is not seeing acceleration. So for him, Newton's law is getting violated. In fact, Newton's law is not getting violated. Newton's law does not hold for him, in fact. He is seeing a force, but he don't see the acceleration. He is seeing N sine theta, but he don't see any acceleration in the wedge. So for his observation, Newton's law does not hold good. But there is one manipulation I can do. There is some manipulation I can do. If in some way I can neutralize, the effect of the acceleration of his frame, then I can apply Newton's second law correlating his observation. If you want to correlate his observation with forces, you have to make certain change. See, there is a difference in A1 and A2. This is holding good. This doesn't hold. Why? Because A2 is different from A1. So if I do something on this side such that whatever term is missing from here, if suppose whatever term is missing over here, you have some term over here which is, you have certain term over here which is missing from here, you have some difference in A1 and A2. So instead of disturbing this A1 and A2, which will be tough to make O2 understand there is some acceleration which he is not observing, right? So instead of changing A1 and A2, if I put something over here such that this term, when you add some term over here such that this equation becomes same, your work is done. And that you can do. How you can do is, you have to, apart from all the forces which you have shown, they are the real forces. Real force means force arising out of interaction. what you can do is, in order to make the two equations same, you have a term some missing over here. A2 has got some term which is different from A1. So if I can make some change on this side and such that this equation turns out to be same, our work is done. And that we can do by applying one more force apart from all the real forces acting on the system. You just apply one more force, that's called pseudo force. You don't need pseudo force when you are solving problem correlating the observation of O1, but you need pseudo force only when you want to correlate the observation made by O2, because for O2's observation, Newton's law does not hold. So if you want to deliberately correlate the observation made by O2 with the forces, then you can do that by applying one additional force apart from all the real forces acting on it. You apply one more force, that's called pseudo force. And the magnitude of pseudo force is equal to the product of mass of body being observed by O2 and acceleration of the frame of non-S observer. Acceleration of the frame of non-S observer. Alright? Acceleration of the frame of non-S observer. And direction is opposite to the direction of acceleration of frame of non-S observer. So I'll apply pseudo force. Suppose I want to write equation of motion for the block according to O2, and I apply pseudo force, that will be acting in direction opposite to the direction of acceleration of the frame of non-S observer. So frame of non-S observer is basically wedge is moving in direction in leftward direction. So I'll apply the pseudo force. Towards right, that will be equal to mass of the body and acceleration of the frame of non-S observer, that is m into capital A. Here also I can apply the pseudo force. Whichever body you want to write the equation as per O2, you apply the pseudo force, and now you are in position to correlate the observation made by O2 with respect to forces. You need Newton's second law. I can use Newton's second law and correlate the observation made by O2, and that we can do by, see, in this case, this wedge, for according to O2, the wedge is in equilibrium. So I can write, see, this is the equation I wrote as per O1, right? Now I write the equation of motion as per O2. I apply the pseudo force. Applying pseudo force makes him eligible to write Newton's second law correlating his observation. So the wedge is in equilibrium, so I can write R minus n cos theta minus mj is 0. Net force in y direction is 0. You don't have any acceleration in x direction as well. So net force in x direction will also be 0. That is ma minus, or better I write, there is no acceleration towards left. So n sin theta minus ma is 0. Here you don't have acceleration in y direction. So the net force in y direction, mg cos theta minus a net force in this direction, net force, you don't have any acceleration in this direction. So mg cos theta minus n, and what will be this? this will also be theta minus ma sin theta is 0, and you have an acceleration a towards x, so I can write what is net force in x direction, mg sin theta plus ma cos theta. And that will be equal to mass into acceleration. That will be equal to mass into acceleration. You have this equation for O2, right? According to O2, you have these equations. Fine. So that's how you can do problem correlating his observation, O2 observation with the forces. If you compare these two equations, do you find any difference? Do you find any difference in this set of equation, this set of equation? You find the equation to be same. The equations are same basically. There is no difference. There is no difference in the equations. Here also this set of equation and this set of equation is same. You won't have any difference in fact. The mathematics won't have any difference in mathematics. But physics behind these equations are entirely different. Here this ma is effect. Is not a force, whereas here this ma is a force. Here this ma cos theta which we are having is a effect, whereas this ma cos theta is the force. This is acceleration, this is force over here. Here this is effect. Effect means acceleration, whereas here it is cause, force over here. So physics is entirely different. Answers you will get is same. So it's on your choice to do the problem. You can do the problem correlating the observation made by O1. In that case, you don't need these pseudo forces. If you want to do the problem as per the observation made by O2, then you need these pseudo forces. Why? Because this person is not eligible to apply Newton's second law. This person is not eligible to apply Newton's second law. So in order to make him eligible, you have to apply these forces. And at the last, I'll tell you, these forces actually do not act. Because if this force would have acted, then it would have been applied by O1 also. You can't have a force which is being observed by one observer and not observed by O2. These are just a manipulation into Freebody diagram so as to compensate for the difference in the observation which O1 and O2 have. There is a difference in the observational acceleration which O1 makes and which O2 makes. But the observation of O2, the observational acceleration made by O2 won't be applicable to that observation. Newton's second law won't be applicable. But then it's not good to convince O2 that his observation is wrong. Actually his observation is not wrong. What he is observing, he is telling you that. So instead of making one observer understand that this is your observation, that is what observation is making is correct. But what we are doing here, we are knowing that there is a difference in observation, there is difference in the acceleration which they observe. So instead of putting any change in A1 observation of acceleration made by O1 and O2, what I am doing is I am manipulating, I am doing some manipulation in the forces. I am doing some manipulation in the forces. See, this term ms cos theta is missing from here. You have the missing term over here. You see the same term is appearing on the left hand side and making this equation same. Getting a point? You have this term which you don't have over here, but the same term is appearing in the form of force over here. You have a term here, have a term ma over here, you don't have any term over here, but the same term appears as the force over here. So that's just a manipulation. That's just a manipulation. And that's just to enable O2, and that is just to enable O2 to write Newton's second law correlating his observation of the forces. Actually the force never acts. Force here is something which arises out of interaction. If this force is acting, then who is exerting this force on the wedge? This must have an answer. If it is a real force, then somebody must exert it on the wedge. And on that wedge will apply a reaction force. We don't have anything. Because you can't have this force without this reaction acting on that. So if this MA would exist, somebody must have acted this and on that body wedge will exert a reaction. Alright, if this MA is acting on the block, somebody must have exerted this MA, but there is no one who is exerting this MA. So this is not a real force, this is a pseudo force. I write in big word, pseudo force, or fictitious force. That's pseudo force or fictitious force. It's not compulsion. You can do the problem as per O1, you don't need pseudo force. If you do the problem as per O2, you need these forces, right? So that's about pseudo force. I'll discuss more